Hello, everybody, and welcome back to episode 2 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike. That is Gavin. Gavin, how you doing today?
I'm good. Just trying to survive the holiday season like we all are.
Yeah, it'd be really great to not end up on this podcast before too long. What are you doing for the holidays?
So like we talked about last episode, I do live in South Dakota for most of the year. Although I did go home, my parents sort of surprised me with a plane ticket back home. So that was my day yesterday. So
You're comfortable riding on a plane right now?
um, being on the plane, pretty much. From what I read, I did lots of research and stuff about flying beforehand,
Hmm.
and the plane itself is pretty safe. It's just being in the airport that sort of sketched me out. But I'm taking lots of
Hmm.
precautions while I'm home. I'm getting tested as soon as possible. So
Wonderful. Well, I'm glad you'll be able to see your family and hopefully do that safely. So as I'm looking at the list today, I think we decided that we were going to begin episode 2, our first kind of episode about something we're going to start talking about dinosaurs, which I'm pretty excited about. So I'm looking at it here. It looks like today we're going to be talking specifically about dinosaurs and their extinction.
yeah, so we talked about it a little bit last episode.
Right, you blew my mind last episode,
Hmm.
which was like, right, apparently, I mean, I think we can go over kind of the usual story, you know, at least the way I understand it. My layman's kind of understanding,
Hmm.
and then you can kind of break down what actually happened. But it was always my understanding that there was the 65 million years ago, the asteroid comes down and hits I think it was the Yucatan Peninsula or
Yep.
something to that effect. Hits that and it kicks up a whole bunch of dust that blocks out the sun. That means that there's no more food left for any of the animals that are left on Earth. And then like 95% of things, including dinosaurs, die out after that. That was always kind of my understanding from what I remember from probably fourth grade science or whatever it may be. So we can start from there, and where have I gone right and where have I gone wrong?
So we can actually work our way up to that because I think it's important
Okay.
in with all things geology. Like you sort of have to start at the beginning because it's like you can't talk about a particular event without
Hmm.
more broadly understanding how the world got to be the way that it was whenever that event happened.
Understood.
So,
All right, so let's where I don't know where exactly the beginning is here. Are we going to the Big Bang or what's
oh no.
happening?
So we will start with a little bit of a lesson on geologic time. So, this episode will get a little technical, not the most technical that we will get on this podcast for sure.
Right. Let's
But
work our way up to it here.
a little bit of a science warning here. So, broadly, um, we'll start with how geologic time works for the last 500-ish million years. So they're different. The largest group of time bins that we use are called eons. Right now we are in the Phanerozoic eon, which basically contains goes from the start of when we start finding complex life to now.
And when you say complex life, can you like what counts as complex life? Multi-celled
Pretty
organisms?
much, yeah.
Okay.
Um, so that goes from the Cambrian period, which is the first period, so the next smallest time bin. Um, in the I guess there's one smaller than Eon. After Eon goes Era. So people use Era incorrectly pretty often. So Eon is the largest scale that we have. The next one is Eon. So Eon, there have been three of them in the Phanerozoic. There's the Paleozoic, which paleo means old, and zoic means life. So it is the old life, the first part of the Phanerozoic. Then after that comes the Mesozoic, which means middle life. That is what we typically think of when we think of the dinosaurs. And then we have the current one, which is called the Cenozoic. Ceno is a weird sort of prefix. It's essentially modern, quote unquote, life.
And how do those distinctions end up getting drawn? Like obviously with all this stuff, it's probably kind of fuzzy, I would assume. But why exactly do we end up drawing a line between the Paleo and Mesozoic? and then the Mesozoic, and what was the most recent one? It was something started with a C.
Yep, Cenozoic.
Cenozoic. Yeah. Like what exactly draws those lines? Is it just a case of like we had to draw the line somewhere, so we picked, or is there a more rigorous method to that madness?
It's a big mass extinction.
Really? Okay. So,
So
do we know what caused those other mass extinctions?
so there's 5 big ones total. We're pretty confident on three of them. And we can do a whole other, episode about mass extinctions. You could honestly do an episode about each of the mass extinctions, like, comfortably. Um, but anyway,
That's something I think I'd be really interested in doing something like that. But if you can give us kind of the Reader's Digest version of kind of the the mass extinction events that caused that break in those different they were different eras, correct?
yes, so the end of
Okay.
the Phanerozoic era, or I'm sorry, I just sort of woke up from a nap, a little sleepy. The end of the Paleozoic era, so the first one, um, that ended at the end Permian mass extinction, which we lovingly refer to as the Great Dying,
Oh, it's adorable.
because upward, like on land, between 95 and 98% of all species went extinct. And in the water, closer, but between 90-95% went extinct.
Okay. Do we know what caused that?
Pretty much, yeah. Gigantic, like, and when I say that, I mean unimaginably large volcanic eruptions for tens of thousands of years.
Good Lord, tens of
Like, I'm
thousands
I'm
of okay.
talking most of modern day Russia covered
Right.
by like a kilometer of lava.
Good Lord. I am looking for
Unimaginably horrible world conditions.
I am looking forward to our episode about this, but I'll put the brakes on right now and we can move on. What about that next mass extinction event that ends the Mesozoic period?
That is the one that killed the non-avian dinosaurs.
Interesting. So I think
Yep.
that's a great place. I guess we'll eventually end up there. But
Yes.
so we have our eras, and we're I guess getting into we're going to be talking about that break between the two most recent eras.
Right. So then we'll sort of focus here on the Mesozoic then. So the Mesozoic starts with the Triassic period, about 252, I believe, is the current date, million years ago,
Hmm.
and then goes until 66 million years ago. It used to be 65, but as we get more, better information, better, uh, different like chemical methods for figuring out, okay, exactly how long ago did whatever event happen. For example, there are radioactive elements in like volcanic ash, or in the case of like the giant meteor impact that caused some radiation. And based on it, we know how long that radioactive element's half life is. So based on that, we can figure out how long it's been since that happened. And as our methods for doing that get better, we get a better handle on when different events happen. So
I find it so interesting that we have the technology we have can be kind of that granular at that far back. Like, I mean, a million years is a long time, but
I'll see
like,
you.
well, right. I mean,
Not to a geologist,
right,
really.
of course, but of course, it's but that's part of what I'm saying is that to a regular human being, that seems like an eternity, but to a geologist, a million years is almost nothing, and yet we have the tools and technology to apparently distinguish between a million years. We used to call that era 65 million years ago, and
Yep.
now apparently it's 66 million years ago. I just find that fascinating that we're able to tell the difference in things at that kind of a granular
Hmm.
level because like you said, a million years really isn't all that long a time.
Yeah, so it definitely gets easier as you get closer to the present. Like, for example, the stuff that I
Of
actually
course.
work with is only about 10 million years old. So usually on stuff that old, we can get a resolution within about 10,000 years or so.
Hmm.
But for stuff around, the time of the dinosaurs, usually plus or minus like half a million years is pretty good.
Okay.
Yeah, so dinosaurs show up in sort of like the middle of the Triassic. So we'll say roughly 180 to 190 million years ago. And
Do we know what the first dinosaur was?
not to my knowledge, it's really rare to have sort of like the first member of any group preserved, just because fossilization is a really picky process. Like people have done all sorts of studies to figure out the odds of just something dying and it being preserved, and it's like worse than 1 in a million.
Oh, really?
But that is highly influenced by where the thing lived. So,
Understood.
in general, places on land tend to erode sediment, which doesn't really, you have to be buried in order to be fossilized. So, if things are
Right.
being eroded instead of being buried, being on land's not a great place to be. Whereas if you're in a shallow ocean, where like at like the mouth of a river or something, where all of that sediment that's being eroded from the land ends up being dumped and then settling, that's a great place if you want to be preserved. So, um, because of that, the fossil record is super, super highly biased toward marine stuff.
And when was it? Yeah, I was going to ask when was it that we first ended up, kind of discovering this bias and try to reevaluate that. But I think we can probably save that for another time.
Yeah, the history of paleontology is crazy, and I would need to do a bit of pre-work before that. Off the top of my head, I don't really know when we started to suss that out.
Exactly. So we can. So I think we can kind of pick it up there, talking about the beginning of those dinosaurs, and we don't know what the first one was, but we know roughly when the dinosaurs came around. About how many millions of years ago was that?
So the last time that I checked, and once I'm sure I will say this several times throughout this episode, I do not study dinosaurs. So
Which is a shame, by the way.
it is a shame, but for reasons we'll talk about probably in a later episode, there's a very good reason that I don't study dinosaurs. Um,
Okay.
we might even get into it a little bit in this episode. Who knows? But
Okay.
so last time that I checked, and people are always looking, just because dinosaurs are a very popular group, people are always looking at different aspects of dinosaurs. So this is a target that's kind of changing pretty regularly. But I would say
Hmm.
somewhere. So the Triassic period started, like I said, about 252 million years ago. I think the first dinosaurs that we are aware of started around 220, 225 million years ago.
Okay.
So sort of in like the middle of the Triassic period, because the Triassic ends with another mass extinction. One of the smaller ones.
So we are dividing both different eras and different periods of geologic history, kind of by mass extinction events. It seems to be kind of a common, line of demarcation to use.
Yes and no, because so like the period at the end of the or at the end of the like the middle period of the Mesozoic, the Jurassic, didn't end with a mass extinction. So generally, um, period boundaries are drawn by you just sort of pick a taxon or a species. Taxon is sort of the catch-all term for you can use that to apply to a species or a genus or a family. Um, but you sort of pick something and you say, okay, if you find it, if you're looking at a layer of rock, because in rocks the older stuff is at the bottom. If you're
Right.
looking at rocks and you find it, find whatever species you use to draw that line. If you find it, okay, cool. Anything below that is, for example, the Jurassic. The last time you find it, anything above that is the Cretaceous in this case. So almost all period boundaries are drawn using species like that.
Really?
Yep,
Okay.
including like the Great Dying. Although I feel like just kind of everything dying is kind of the marker for that.
Yeah. Yeah, you can kind of pick your species at that point.
Pretty much. But yeah, so dinosaurs show up around 220, 225 million years ago. And for the most part, you would be able, well, most people sort of see extinct reptile thing and automatically assume it's a dinosaur, which is not at all correct.
You preempted my next question. Actually, I was going to ask. So we're talking about dinosaurs. What kind of makes a dinosaur? Because I think everybody kind of has that image in their head of a Tyrannosaurus Rex or a Triceratops or
hmm
a Velociraptor. or any other kind of dinosaur they may have seen growing up. But what actually, my understanding is that there's a broad range. There's dinosaurs that fly. There's larger dinosaurs and smaller dinosaurs. So how do we know we're looking at a dinosaur, and how do we know that we're not looking at something else?
That's a really good question. So dinosaurs, and this is gonna blow some people's minds as well. So the first dinosaurs were all bipedal.
We walked on 2 feet.
Yep, even the ones that
Okay.
ended up becoming the big long neck sauropod dinosaurs, they were bipedal. One of the defining characteristics of dinosaurs is having what's called an antorbital fenestra, which is basically a hole in your skull. Ant meaning in front of your eyes. So if you think of like a T-Rex skull, how if you're looking at it from the side, they have where you can tell their eye goes, and then sort of down their face toward their nose, they have a big gap in their skull.
Okay.
That is a defining characteristic of dinosaurs. And then the one of the most diagnostic things of especially early dinosaurs is they had really unique ankle morphology, like the bones in their ankles were really, really unique. And that helped them be much more efficient at running bipedally. They were the first group to really do bipedalism well. And a lot of physiological things that we can tell from like looking at their bones. Their bones, especially the early ones, were pretty light. And we can tell by some weird features that like you can tell from the bone, but apply mostly toward like their muscles, their soft tissues. But they need significantly less water than a lot of other things at the same time as
The
them.
bones do, or just the dinosaurs in general do?
Dinosaurs in general,
Okay.
which is one of the big things that people speculate that might be why they were so successful. Because, at this time is when Pangaea was really a thing. Pangaea wasn't around for the entire time that dinosaurs were around, but when dinosaurs first evolved, Pangaea was in full swing. And
And if I may, really quick, just I think I can even explain this one
yeah,
for anyone who's not sure of what it is. But Pangaea, you've got all the different continents and land masses on Earth, and even now today, they all exist on plates. They all kind of move around at this incredibly slow pace for any human to see. And at one point, all of these continents were all smushed together, called Pangaea. There wasn't seven continents or six or however you might want to divide them up and count. They were all together, so you could walk on foot from the farthest point on land to the other farthest point on land, because again the whole landmass on Earth was connected. How did I do?
pretty well. Yeah, that's pretty much correct. Obviously, there were islands and stuff, off the coast, but
Of
um,
course, speak.
yeah.
You
But
know,
for the most part,
I felt smart, but
yeah, no, absolutely though. That was a pretty good definition. But the thing with Pangaea was, so if you think, we'll just talk about North America, for example.
okay.
The coasts, well, yes, like sort of the southwestern coast around like the LA area doesn't really have that much water in general. Coasts are pretty wet places, even sort of up in the northeast. We still get rain. You know, Technically, the place where I grew up is a temperate rainforest. We get just enough rain to qualify as that. Um,
I did
so
not realize that.
technically, yeah, that's how it should be. Without like humans cutting down all the trees and everything over the last couple hundred years. But technically, that is the environment that we live in. However, once you get more toward the middle of the country, such as where I normally live in South Dakota, it's very dry. And this was definitely the case with Pangaea, only on a much larger scale.
Because there's a lot less coastline.
Well, there's a lot more coastline, but because it's just so huge, but proportionately, you just have a lot farther to go to get to like the middle.
Right. Okay.
So essentially, the middle of Pangaea was almost unlivable. There was, from what we can tell, nothing there.
Right. There was no easy access to water
Right.
there, and you would be traversing what today we would think of as continent long distances just to get water. So it wouldn't make any sense to especially be a rather large organism and living that far
hmm
away.
Well, the first dinosaurs really weren't all that large. They were maybe somewhere between like chicken and like medium dog sized.
Really?
Yep. Very quickly, some of them got quite bigger. So if you think of Dilophosaurus, one of the more famous Jurassic Park dinosaurs, the venom spitting one with the frill. The only thing that they got right about Dilophosaurus is its name, and then it does have two crests on its head. That's what Dilophosaurus means. Those are the only thing they got right about it. Dilophosaurus actually, in its time, was about 10 feet tall, and probably the top predator on Pangaea
Wow.
at the time, or at least a contender for it. And obviously, there's no evidence for them spitting venom or having a frill. There's no evidence for that whatsoever.
I figured there might be a little bit of artistic license. And just a quick kind of preview. I think our plan is to record this episode, and we will eventually get to the extinction event of the dinosaurs and what we do and don't know. But I think we're planning on this week releasing, our episode on dinosaurs that you're listening to now, and then next week we're going to talk a little bit about Jurassic Park and what they got right, what they got wrong, and how that's partially how that affected Gavin, which we talked about last week, but how that affected science in general. So this is going to be, you can almost think of it as a spiritual two-parter, even if they are kind of two different things.
But yeah, so the dinosaurs started sort of a little after most people think in general, started a lot smaller than most people think, and didn't really take off until the start of the Jurassic. So in the beginning, so there were two big groups of dinosaurs. And so there are the group called Saurashia, which means lizard hip, because a bone, the pubis, the bone in your pelvis, looks similarly to that of a lizard, which is what saur means. Saur. And then there's the ornithischians, which means bird-hipped dinosaurs, and their pubis points sort of backward, like it does in birds. However, weirdly, birds evolved from Saurischian dinosaurs, so that actually evolved twice. So the Saurischian dinosaurs are your theropods, the ones that walked around on two legs and ate meat, T-Rex, Velociraptor, and such. And the sauropod dinosaurs, the biggest land animals ever,
Right.
Long necks, long tails. So those two groups are...
Are we talking like T-Rex here?
So T-Rex is a theropod dinosaur, yes.
Okay.
But the sauropod dinosaurs are things like Brachiosaurus, the massive plant-eating ones.
Right, with the long necks, right?
Yep, long necks, long tails. One of them can be the size of a herd of elephants, pretty much. So those two groups are the most closely related or to each other. Then in the other group is every other kind of dinosaur. So you have your Ceratopsians, like Triceratops, with horns, frills, and such. Then there's ornithopods, things like Edmontosaurus, Maiasaurus, Hadrosaurus, Iguanodon, your duck-billed dinosaurs.
Mm-hmm.
And then we have things like Stegosaurus and Ankylosaurus, your like armored dinosaurs. Those are all ornithischians.
And is that sort of like a catch-all? Like, we've got our distinct categories, and then kind of everything else that's left we're going to put into one category, or do they have kind of a defining characteristic?
Yep, it's the hip thing, basically.
Okay, gotcha.
So there are very few things that... Dinosaurs were a very diverse group, but most people think, okay, big extinct reptile thing, that's a dinosaur, which is not at all true. So for example, none of the following things that I'm about to say are dinosaurs. Things like mosasaurs, the big thing from Jurassic World that, ended the movie by eating the big bad dinosaur. That is not a dinosaur. That is actually a lizard. That is a true lizard, whereas dinosaurs are not true lizards.
So it's a real thing. They just like it's not a dinosaur.
Right. I mean, theirs was a little big. Theirs looked to be close to 100 feet long. The biggest one that I'm aware of was about 60. Still really, really big.
Okay. So some artistic license, but they broadly had the idea correct, I guess, but it's not a dinosaur.
Exactly. So those are pretty closely related to like monitor lizards, is what we're pretty sure they evolved from, or something similar. So basically, if it lived in the water, with one very notable exception, it is not a dinosaur. So things like Plesiosaurs, the sort of Loch Ness Monster looking ones with the four flippers and the long necks, those are not dinosaurs. Those are not even closely related at all.
What do we call them? What are they?
They are Plesiosaurs. They are their own thing.
Okay.
They are on
a group of one.
Pretty much. They are more closely related to lizards than they are to dinosaurs. So like the most closely related things to dinosaurs are crocodilians, at least of what we have today. The most closely related things to dinosaurs, but are still not dinosaurs, are pterosaurs, things that could fly, quote unquote pterodactyls, even though that is not really a real term. Um,
Okay, so I've got like 9 questions here, but
go
pterodactyls aren't
for it.
dinosaurs?
They are not dinosaurs. They are
Really?
the closest relatives to dinosaurs, but they are not dinosaurs.
And so what again is it again that hip bone or what is it that, makes that distinction?
So pterosaurs are weird. In fact, most things that fly are weird in that we do not have a good record of how they became able to fly.
Hmm.
The way my advisor, because we had a whole lecture about, he called them volant vertebrates, which just means able to fly.
Okay.
So that is pterosaurs, birds, and bats. Birds are the group of those three that we have the best record of how they became able to fly, and even then, the record's not good because the way he phrased it was things that quote unquote decide, because evolution doesn't work that way. You don't just decide to do something and then it happens.
Right.
But things that go down that path commit to that hard because there are so many adaptations needed to be able to fly that you can't just get one slowly and then get another one slowly and then end up being able to fly. That's something that your lineage, again, quote unquote, devotes itself to.
You need to like, go all or nothing. So I assume if we're looking at the
Exactly.
fossil record, you'd be able to see,
Hmm.
like all of those, necessary adaptations for flight occurring all at once. Is that about right?
Right. It's like you see we have something that we think is a non-flying ancestor to pterosaurs, but the next thing we have was, from what we can tell, fully able to fly. Because, you're not going to get hollow bones by itself, really. You're not going to get a super long, because, pterosaurs fly, their wing is essentially just a super long ring finger. You don't do that without being able to use it to fly.
Right.
So it happens so quickly that, like I said, preservation and fossilization is super rare. So like it happens so quickly that there's just not enough time for that to really be preserved.
Mm-hmm.
But we know that they're most closely related just because of similarities with like I said, with their ankle morphology, a lot of other just general characteristics. When they show up is also pretty useful as well. Like I think there's some things for like the backside of the skull that are also pretty similar between pterosaurs and
So is it
dinosaurs.
the basic idea? We can tell they're pretty closely related because of when they showed up, because of the ankle, because of their skulls and everything. But is it just those characteristics of flight that make it kind of force us to categorize it as something distinct from dinosaurs?
Yes, absolutely.
Okay, perfect.
But yeah, so pterosaurs are not dinosaurs. Anything that lived in the water is not dinosaurs, with the exception of, we think, Spinosaurus.
Why do we include that as a is it well, first off, let me ask the sort of the opposite question. So we talked about flighted dinosaurs and why they're not actually dinosaurs. Is it a similar thing for kind of what we would what the layperson would call a marine dinosaur, or dinosaurs in the water, like the adaptations necessary to live in the water, and kind of cause you to be just a different thing, the way we categorize different groups of animals? Is that kind of why like water dinosaurs aren't a thing just definitionally?
So with dinosaurs, no. From what we can tell, dinosaurs were a very diverse group. They even did have some members that can fly, birds. But being aquatic just seems to be something that they just never did, with the exception of things like penguins. So it would not surprise me that, if we were to one day find something this is clearly a dinosaur, it meets all the criteria to be a dinosaur. It has that antorbital fenestra. It has other parts of like the back of the skull where it sort of connects to the vertebrae. It has the ankle stuff. And it lived in water. It would not surprise me. However, we have not yet found something like that. And to my knowledge, we just I don't believe that we will, but if someone found a fossil like that, it wouldn't surprise me.
Okay, so it is like they are not necessarily mutually exclusive, being in the water and being a dinosaur, but it's the situation in which that animal would arise and would have existed requires a set of circumstances that's rather unlikely. So that brings us to kind of that one dinosaur that kind of was in the water a little bit. Can you just quickly tell us about that one and why why we have the one special snowflake here amongst the
Yeah,
dinosaurs?
for sure. So Spinosaurus is something is very weird, and this is stuff that is only coming out relatively recently. Partially because most of the good fossils of Spinosaurus were destroyed in World War II. They were held in some museums in northern
Hmm.
Africa, and I believe some was held in Germany as well.
God, that's tragic.
And this was something that the Allies actually destroyed, I believe.
The Allies were the bad guys.
In well, okay,
No one
don't
take
take
okay.
that,
No one
listeners.
take that
Don't
out of
take that out of
context.
context.
There's going to be an issue here. So, for the record, I'm very specifically talking about museums and fossil records here. I am not talking about anything else that came to your head whenever we're talking about the Allies being bad guys.
Yeah. So it was over the years we sort of went from Spinosaurus is this big predator similar to T Rex, and then we're like, okay, no, it probably ate fish and lived like uh around water. And from that we sort of knew that from like its tooth morphology, and it has this really long skinny snout, which is typically what you see in things that eat fish. Then we sort of started finding like little pits on the snout, which we think are used for like electroreception, which does not work in air. It only works in water. And then recently, I think they found some new tail material that appears to be like have some spines on it as well that look like it would support a tail similar like an alligator tail that has it's like pretty narrow and tall to use as like a paddle to swim. And then I think people have been doing some different isotope chemistry stuff on their bones, and based on that, you can tell pretty much where they lived and where they spent a good chunk of their time.
Okay.
So I think it's pretty conclusive that Spinosaurus spent most of its time in water.
And it meets all those other characteristics of actually being a dinosaur, which is, we're very confident. When I say we, again, people who study this are, rather confident that they spent time in water, but they meant, or they spent, a lot of pardon me, they meet all the criteria to actually be a dinosaur. And I mentioned, I mentioned people that actually study this a whole lot. You actually, we've been talking this whole podcast about dinosaurs, and you mentioned last time that you don't particularly care for actually studying dinosaurs, even though you, like everyone else, I assume, first got into the field because of that. So why is it that you would prefer not to study dinosaurs a whole lot? Do you just not like it? Is there something about the field? Do you don't mind it, but there's something in the field that you're studying that you like more? What is it exactly that that kind of takes you away from studying dinosaurs?
I want to be as nice with this as I can. Dinosaur paleontologists.
Go on.
Because of Jurassic Park, dinosaurs became very popular. I mean, they were always pretty popular, but because of Jurassic Park, dinosaurs became essentially in the collective public's mind the same thing as dragons. And
As a noted dragon fan, I support this wholeheartedly.
so people just started treating them as something other than what they were, which is just another, albeit really interesting, group of animals. And people were getting into paleontology because they loved dinosaurs, not because they loved science. And so it's it's not nearly as bad as my advisor makes it sound like it was in sort of like the late 90s through mid to late 20 or like 2000s, through like 2009.
In like the direct aftermath of Jurassic Park, I take it.
Exactly. And then he even did his master's thesis on dinosaurs, on long neck dinosaurs, sauropods. So he likes dinosaurs. But dinosaur paleontologists for a long time were just doing really bad science. Because when they were coming up, they did not care enough to put in the hard work that science requires to do good, valuable science.
So has that harmed like the study of dinosaurs to this day? Is that something that, people were doing bad science, but you also had kind of the stalwarts of the field that were still doing lots of good work? Is that, like how has that affected the actual field of dinosaur paleontology that you have this generation of people that I assume with the best of intentions, but they're not doing the appropriate legwork and the appropriate kind of science for the field. Is that irreversibly damaged the field? Is it lasting through today? Like how has that affected the field?
Part of it's definitely lasted through to today. It's definitely gotten better, but a large part of it is ego. So like people sort of think as scientists as these nerds who sit in their lab coats looking at a microscope, which like is true, but they also have egos. And so landing like a really cool interview or like being on like a really cool documentary sort of makes your head get a little big. And people rarely want to hear about the Great Plains, like what I study, about 10 million years ago, which fundamentally don't look all that much like different than they look today, when they can hear about 20-foot tall monster that ate other monsters. So because the public cared more about dinosaurs, dinosaur paleontologists sort of also only cared about what other dinosaur paleontologists said.
And it sounds as though, like, when you're saying this, like, there's both kind of that bias. So we have like a bias. It sounds to me there's two kinds of biases, I guess is what I'm saying. We've got the first bias towards people that go into paleontology or going into dinosaur paleontology because it's the cool trendy thing to do. And then there's kind of a second kind of bias where amongst people that go into dinosaur paleontology, there's sort of a bias towards sensationalism and a bias towards trying to kind of feed that narrative of dinosaurs are dragons essentially. And the more you can do that, the more you can say dinosaurs are dragons and they're these big monsters and this, that, and the other thing, that you're able to get on TV shows and you're able to become more famous. And so you might not, I assume that people aren't intentionally lying. I wouldn't want to accuse anybody of that, but there's kind of a bias towards the more sensational elements of the field. Is that kind of that two-track bias, is that part of what has kind of brought down the field to an extent?
I think that sounds right. So one of the more egregious things that is a good example of this. So Brontosaurus is a very well-known dinosaur.
I know Brontosaurus, which like tells you all you need to know because you have named several dinosaurs today that I've never heard of them ever. And I know Brontosaurus, plant eater, long neck, stood on four
Yep.
legs.
So that is a sauropod. However, Brontosaurus is no longer a valid name. Brontosaurus does not exist. So originally, and we will get to this in a future episode, but back in the late 1800s, a lot of bad paleontology was done, and back then, people just sort of this new thing that I found in the ground is very slightly different than this thing that somebody else found, but I want to add another name to my list. I want to name something new and chalk that down as something new that I found that this other guy didn't find. So they named it Brontosaurus when it realistically is a Apatosaurus. That is what Brontosaurus specimens that were named back then are now called. And granted, that's not as relevant to today, but the fact that Brontosaurus has not been a thing for quite a while until I think we read a paper in one of my classes from 2014 or 2015, I think, that sort of brought back Brontosaurus.
Explain what you mean by that.
Basically saying they found this specimen and they did a couple analyses on it comparing it to Apatosaurus specimens that are actually Apatosaurus and sort of compared them to them in a very like analytical, very a way that works if you do it well, which these people did not, and said this specimen is different enough to justify calling it Brontosaurus again. So that paper got a lot of news because it brought back Brontosaurus as a valid name to call this thing, when in reality it is not. Their methods were bad. They did it on like one specimen, which a lot of people got away with back in the day, but naming something totally new off of a single specimen is generally kind of frowned upon these days. It's still done, but not as much. But they basically added that in, and that wasn't even the main goal of that study. It was something that sort of threw in my opinion, to draw more attention to their paper.
To draw more attention to the paper,
Yes.
and now the general public that isn't studying this so much, they see an article that confirms the Brontosaur, probably in their head. I know certainly if I saw that, I'd be like, yeah, the Brontosaur exists, and now we have independent confirmation. And anybody who saw that story and remembers that story from all that time ago probably wasn't looking at any of these subsequent research or things that other scholars have said on the matter, which is apparently that Brontosaurs don't exist, which is something that's a little mind-blowing to me, that's a whole category of dinosaur that is so distinct in my head,
Well,
that is really just another dinosaur.
it's not like that big of a category in that it is one genus. Brontosaurus is one genus. Apatosaurus, very, very similar dinosaur, and in my opinion, the same. Like, Apatosaurus is what people actually mean when they say Brontosaurus. The same dinosaur. Very big, long neck, 8 plants, 4 legs, long tail, same thing. And that happens very often. Like I said, back in the day, and I have a whole episode planned and laid out about that bad paleontology done at the end of the 1800s, of people just saying, this is very slightly different, but I want to name something new, so I'm going to call it something new. We systematically work and fix that by analyzing them and say, okay, these two are different, but they could be different. Just so this one could be a male, this one could be a female, this one could just be in a different area than the other one. Like, for example, brown bears or grizzly bears. The grizzly bears that live in like Alaska are like 50% larger than the ones that live in like the Rockies, but they are the same species. They're just a different location variation of them.
So if I may, I think I think I understand what this is. If I could sum this up and then tell me if I'm correct. Like it is possible to draw a distinction between Brontosaurs and the other one. Like you can find a distinction to draw if you are looking for it. However, the distinctions that are available probably aren't great enough, or not the right kind of distinctions that you would need in order to actually classify something as a new species. Is that about right?
A little more technical than that, but basically, yeah.
Okay. Well, we're going to keep this as
Yes.
simple as
Yeah.
possible for me. So all of that, if you want to kind of put a bow on this, but kind of this history of bad science for decades at this point is kind of what has driven you away from this
hmm
field.
So, in general, and I want to be very clear, there are some very good dinosaur paleontologists out there.
Absolutely, and I wouldn't want to trash that. All the good work that that people are doing, including people that may have gotten into it for for the wrong reasons, but have changed what they're doing. I certainly want to commend anybody who's doing good
hmm
work in that field or any other.
Exactly. And like, there's somebody. So I'm gonna be very clear. I've never met him. I've never talked to him. But a couple of my classmates have, because they did their undergrad work at the same place as him. But his name is John Scannella. He's at University of Montana. He's doing really, really awesome work. However, the John Scannellas of the world are kind of few and far between, from what I have gathered. And the biggest thing is that s- science does not very easily lend itself to big, broad conclusions. You know, Finding something like Spinosaurus being aquatic has been a very long time coming. However, anybody who like only loosely pays attention, it sort of seems like it's been this really big, broad thing that we just found out. When it's like it's sort of we've been working up to that for 20 years now. But some other people working in dinosaur paleontology can sometimes make these really big conclusions that the data just don't support, you know? Or, for example, my advisor, now works on mammals. I said he used to work on dinosaurs, and he did, but he now works on mammals. He went to a conference where somebody presenting some stuff about dinosaurs was making mistakes that like mammal people figured out were mistakes 15 years ago, but the dinosaur people just don't want to listen to the mammal people because they're not as popular and don't know their stuff.
And that's just got to be so incredibly frustrating.
It is, and I want to be very clear. This is I said I don't like broad generalizations. That is a broad generalization. There are lots of good dinosaur paleontologists out there. Most of the ones who got in it for the wrong reasons have since kind of realized this is probably not what I should be doing, and there are not as many of them around anymore. So dinosaur paleontology nowadays is pretty much okay.
Which I think brings us to kind of what we ultimately want to talk about here, amongst those dinosaur paleontologists that are doing things the right way, and amongst the good science that has been done, kind of trying to sift through everything else. We kind of arrive at the end of the dinosaurs, and I kind of told the story as I knew it at the beginning, where the asteroid hits in the part of Mexico, the Yucatan Peninsula. There's a bunch of dust, blocks out the sun, and everything kind of goes away. But what does I don't know if that was junk science. I don't know if that was good science at one time. But as we learn more things, sometimes science changes, and that's a feature, not a bug, as I understand that of science. But what do we know now about the extinction of the dinosaurs?
So, like you said, it's kind of a feature, not a bug, that science works slowly. And this was definitely true of us figuring out about the meteor impact to begin with. So the guy who sort of initially discovered it, or posited that question, was a guy named Alvarez, and in like the mid '80s.
But we have Alvarez here, who you said back in the '80s was kind of the main guy, along with the rest of I assume. Is it a he?
Yes.
So I assume the rest of his team popularized this asteroid theory for extinction.
Right. And so that was a pretty sensational thing, and like I said, one of the few times that we've sort of been like, just that revolutionized what we knew about the end Cretaceous mass extinction. Because before, we had sort of kind of assumed, because by that point we knew what had caused the end Permian one, where close to 99% of all things died. We knew that was extreme volcanism. We knew that the end Triassic one was also some pretty extreme volcanism. So we sort of assumed that there was some pretty extreme volcanism happening at the end of the Cretaceous too, and there was. Not as much as those two other times. But then I don't remember, and like I have read that paper where Alvarez first published this idea, but I don't remember exactly how they found the crater, because it's in the ocean,
like Gulf of Mexico, right?
Yep. So
okay,
I don't remember exactly how they found it, but they dated the rocks to it, and then also sort of if you go to the right places, you can find this really weird layer of sediment that contains an element that's very, very rare to find on Earth, but is pretty common in asteroids, called iridium. And based on some other like radioactive dates, they sort of dated that to around 65 million years ago, which was roughly when they stopped seeing dinosaurs, besides birds.
So there was some correlation here, but correlation, not causation. So they found an asteroid impact that that did strike Earth. That you're saying that did happen, correct?
Yep.
So it sounds as though there's a little bit of correlation, not causation, where we know there was an asteroid impact at that time,
mm-hmm.
and we know that dinosaurs went extinct at that time, and so they kind of drew that line there. And it sounds as though you're about to tell me that maybe that line's a little bit fuzzier or doesn't exist than Alvarez may have thought.
I would say the line definitely exists. It definitely was not as cut and dry as big rock hits Earth, everything dies, because life just is not that simple. So
right,
it takes a gargantuan thing to really impact life on Earth as a whole, And you might think a pretty big asteroid hitting Earth is pretty gargantuan, but if you ever look up a geologic map of Iowa, if you get the chance. This seems random, but stay with me.
You know what?
Um,
do you actually want to do this right now?
Yeah, go ahead.
Okay, I will ignore my typing. You go ahead.
So you will see up in the northwestern corner.
You say Iowa or Idaho?
Iowa.
Iowa. Okay.
You will see up in the northwest corner a series of circles. That is from a meteor impact. Like there was, and also a Cretaceous one. There were multiple of them. This one was a smaller asteroid, but we don't really see this having a real notable impact on extinctions and things. Obviously, it was a pretty bad day for stuff in that immediate area, but just because a big rock hits the Earth, that doesn't mean it's the end of days, like it is at the end of the Cretaceous. A lot of people think that dinosaurs were already sort of not doing so hot at the time, whether it was disease, like some people have speculated, although that's really hard to tell with fossils, just because
disease doesn't fossilize.
Exactly. You know, so we do see sometimes, like, if an animal had like bone cancer, you can tell that, you can see that. And that's actually a whole subfield called paleopathology, which is super fascinating, but something that I don't know all that much about. But there are quite a lot of diseases that you can tell from bones, but a lot of them you just can't. And so that's a really hard hypothesis to test. And also, some people were just sort of thinking that there was some other volcanism. For example, in India, there was some pretty active volcanism as well, called the Deccan Traps, that was not as big as that stuff that I was talking about in Russia with the end Permian, but was still pretty big. And the way it's sort of been explained to me is that obviously this thing didn't help, you know. It's not like
right.
a giant asteroid hitting the Earth would be a good thing for dinosaurs.
It'd be cool to watch.
Oh, it'd be super cool to watch. But was this the... I think it's sort of phrased as, this is a nail in the coffin, not the coffin itself.
Understood. So this was, it was a thing that happened, and we don't want to throw the baby out with the bathwater. This is a piece of the puzzle, but there was other stuff going on. And you mentioned disease kind of as one other piece of that puzzle. What else do we know of at that time? You said that, did you also say there was also some, volcanic activity?
Mm-hmm.
What else was going on at that time that we think, kind of all came together, and were all of those nails that eventually went in the coffin?
So by the end of the Cretaceous, Pangaea was pretty well broken up. By this point, I think South America and Africa had just separated. And I mean just as in within the last 10 to 20 million years. But there's a lot of rifting, which exposes a lot of, imagine shoving your hands all the way down to like the molten part of the Earth and pulling apart.
It seems dangerous.
Right. And pulling it apart.
Okay.
That's essentially what was happening. And so if you're displacing that, some stuff has to come up from the middle of the Earth to fill that gap. And that is magma, which is generally pretty bad for life. Obviously in its immediate area, but magma, especially magma from like the deep core of the Earth, has a lot of really bad gases that it gives off when it comes to the surface. Mm-hmm. Things that cause, I know a lot of people who don't believe in global warming caused by humans are like, oh,
they're not listening to that. I promise you, anybody that is listening to this podcast is like, no, yeah, global warming, huge problem.
Right, but also we need to understand the arguments being made against it if we want to fight against them as well. But
do we need to?
Yeah. Anyway,
okay.
That's a whole other thing. That's like combating conspiracy theories is tough, but it's basically you need to meet them where they're at and slowly sort of disprove things slowly, not just shut them down completely, because then they're just going to write you off entirely.
This can be a future episode of I Wish You Were Dead, where we actually look to the future when everything is dead from global warming.
Yeah.
But so we have these noxious gases from magma.
Right. So these are generally pretty potent greenhouse gases. So those would increase the temperature of the Earth, which a lot of people note The warmest time period, at least from the data we have, which is a very large theme in paleontology and something I'll sort of circle back to in a little bit, the warmest time period that we have on record is the Paleogene, which is the first period of the Cenozoic. So right after the dinosaurs go away. So all that volcanic gas caused a long-term global warming effect even after the dinosaurs were gone.
Okay.
So this was a pretty strong influence in the world at the time. But also, like I said, circling back to that sort of lack of data, I mentioned in the first episode that the only place that we have late Cretaceous fossils is Western North America. And that was not technically true. That's the only place where we have terrestrial late Cretaceous fossils. We have marine fossils, because like I mentioned, marine fossils are much more common than
Right.
terrestrial fossils. So we do have.
Do you still kind of see a trend downward? Do you still kind of see that trend downward in the number of fossils, though? Like, even though, there are some marine fossils that exist, like, is it a pretty noticeable trend downward?
It depends what group you're looking at. In general, yes. However, things like clams were doing fantastically in the Cretaceous and continued to do fantastically afterward. And the reason why we use clams is because they're all over the place. They preserve super well, and there are lots of different kinds of them. So you can get a lot of information from clams. And so lots of other things did go extinct, like ammonites, the like swirly shelled squids, essentially. Those went extinct at the end of the Cretaceous.
Right.
They were doing fantastically up until the end. There wasn't, to my knowledge, a sort of decline. They were not already on the decline by the time the asteroid hit. I think it's pretty conclusive. And again, I am not an ammonite expert, but from what I've seen, there's a pretty direct correlation between asteroid impact, ammonites are dead. Other groups,
Okay.
especially terrestrial ones, we just don't have the information to say. So like in South America, for example, we don't really have, to my knowledge, South America has historically been pretty underexplored in terms of paleontology relative to like North America, Europe, Asia. To my knowledge, we have no late Cretaceous stuff. We have some like middle Cretaceous stuff, which has the largest of large sauropods, that are like almost whale size. And so there's stuff from there, but not the stuff that we need to be like, okay, were there even dinosaurs at all outside of North America when that asteroid hit? We have no idea.
It's important what you mentioned before about that, with the fact, like at this point, Pangaea, was more or less not a thing. The continents had,
Right.
had broken up. So that actually means something to say, only in North America, because if there was, if dinosaurs were sort of on the way out and there was one particular part of the world that dinosaurs were clustered in, they would be there. They really wouldn't be able to walk across and get to other parts of the world at this point. So it sounds as though dinosaurs were already kind of on their way out for one reason or another. North America was kind of a last vestige for them, one of the last places they could actually survive, based on because of whatever the conditions in North America were at that time. Is that is that kind of, again, suggestive evidence? Nothing's conclusive, but that dinosaurs were clearly on the way out well before the asteroid impact ended up hitting Earth.
So that brings up a really, and I'm not meaning to call you out here,
Please.
that brings up a really important logical fallacy.
Oh, what did I do? What did I do? What did I do?
Absence of evidence is not evidence of absence.
Okay.
We do not have rocks from this time, so we cannot have fossils from this time. If we had rocks from, say, 67 million years ago, right before the asteroid hit, in Europe or Africa or Australia, that did not have dinosaurs in them, that would be one thing. But we don't. We don't even have the rocks there. So they could have been everywhere, but we don't know.
Okay, I see. So this is just a genuine black hole. It's not as though we've been able to do the geological research, and we just don't find anything. And again, I'm using the royal we here just so
Yes.
everyone is clear.
Yeah.
But it's the fact that there is a period of time that is just kind of this black hole in various spots on Earth of paleontology, and because of that,
Yeah.
we just cannot say anything conclusively about the existence of and well-being of dinosaurs for this period of time leading up to the asteroid impact.
Exactly. And saying I don't know is something that everybody struggles with, but is so incredibly important in science. And granted, we usually phrase it a little nicer than I don't know, but saying we don't have the data to properly support this type of conclusion, either way, is really important because then you're like, okay, where can we look for these rocks? Now that we know, we need to find them. Like, they're probably out there somewhere. Like, it would not surprise me if tomorrow somebody published a paper finding like a really great late Cretaceous exposure in Africa or South America, because those are traditionally the two continents that are the least heavily explored paleontologically. That would not surprise me, and that would be amazing. However, until that happens and we get good global data, we cannot say either way whether dinosaurs were doing great when the asteroid hit or whether they were doing are already on their way out. We do not know. There's been there's a study published this year. So like in terms of science, basically yesterday.
Which is the year 2020, in case anybody's listening to this in the
Yes.
future.
So doing sort of an analysis through time of the Hell Creek Formation, which is the latest Cretaceous formation here in North America, and sort of the formation below that, and sort of looking at diversity from the bottom, so the oldest part of it, and working your way up toward the end, and seeing, okay, with what we have, how were these specific dinosaurs in this specific area doing? That kind of study is fine. That kind of study is perfect because they specifically state we're looking at just this area and we are only making conclusions about just this area.
You're not trying to say things about things you weren't looking at.
Exactly. And they seem to be like dinosaurs were pretty much doing fine, at least these ones. So who knows? At the end of the day, that's the answer that we have, is that who knows?
So we have a black hole in some parts of the world. Before then, there was possibly some evidence to suggest that they might not have been doing okay because of volcanic activity and disease, but there's nothing conclusive to be said on that. Is there anything else that we need to know about this period of time on Earth, around the time when dinosaurs went extinct, that might, help us, put together those final puzzle pieces?
That is a really complex question. Finding better, even non-fossil bearing rocks would be helpful, because then you can do some chemistry on them in ways that I don't know because I'm not a chemist, but to figure out climate things. And so we broadly know what the climate was like in this area because we have rocks from there. And but so if the climate was doing okay here, because as we know from today, climate change does not affect everywhere equally.
Right.
It does affect everywhere, but not the same. So this could just be an area where the climate change that was happening due to all this volcanic outgassing was affecting it not all that much. Whereas some place that was more toward the poles, in really, really high latitudes, that could have been affecting them a lot, but we don't know.
And so I think that's, when we went into this episode, I was sort of expecting to, sort of expecting to hear, it's more complicated than just the asteroid impact. There are all these other things, and when you put them together, you get this clear picture of how dinosaurs died. And it's more complex, but it's an easy to follow story. But the understanding that I'm getting from you is that it is it is, a complex story to the point of we don't actually have all of that puzzle pieces, or we cannot right now kind of write that cohesive story of why there are no longer dinosaurs. We have to be, kind of content to say right now we have a couple of factors that are going into, or that likely went into, dinosaurs going extinct, but we just cannot write one cohesive narrative about the extinction of the dinosaurs. It's probably that there were multiple reasons and possibly different reasons for different types of dinosaurs or dinosaurs at different locations. So it sounds as though, if I have that right, we have on some level, maybe an unsatisfying conclusion that we just like we do not have that full narrative right now. But yet on the other hand, this is how science works. You don't always get those perfect conclusions, and there's always more kind of building blocks to put together for the next generation of scientists. Is that kind of the end result that we're looking at here?
That's absolutely right. It is a perfectly acceptable answer, like I said, in science to say we don't have the data. And, people just by nature want sort of like a dichotomy. Like either dinosaurs were doing well beforehand or they weren't. The asteroid did kill the dinosaurs or it didn't. And that's just not how science works. One of the things that we do know for sure is that whatever the mechanism for this extinction at the end of the Cretaceous was, is that it was very selective for killing really big things. So, and I think I talked about this last episode too, when we were sort of on this tangent about the end Cretaceous extinction, was that pretty much anything over roughly 100 pounds ish, and that might even be a little bit of an overestimate, went extinct. With a couple exceptions, like things like crocodilians seemed to do pretty much okay afterward, but that is mainly the reason why we have the only dinosaurs that we have today are birds, because birds are small. And birds can fly a really long ways to find food.
And so I think that's kind of a good place to end this episode where we are, is to kind of leave it at the best place that we believe science has for us right now, which is to say that what at least I was taught in school, and what I assume many people listening were taught in school, is like many things that are taught in our schools, an oversimplification, not necessarily wrong, but a gross oversimplification of what was going on. And we know it's an oversimplification for many reasons, but not the least of which is that we don't have the whole story. We don't have everything that happened. We've got a couple of pieces. We know a couple things about the Earth at that time, and we know kind of the effects of whatever all of these factors combined was that basically anything over 100 pounds or so ends up dying out, and we can kind of pass that on to our next generation as this is what we're starting with. Go find more data.
Exactly. Science is always an iterative process. It is always building on itself. And sometimes just straight up saying, hey, this thing from before, that's not right. Which, we talked a lot about climate change in this episode, but like back in like the 70s, early 80s, they were like, oh, Earth's actually getting cooler. No, that's just bad. Your data were bad. And so you can sort of fall into a little bit of a trap of people being like, oh, well, science is all science is nonsense then, because they would point to this old thing that is currently outdated. And I'm like, well, no, it's not nonsense. It's just that those people were working with bad information.
And that is always something that's frustrating when it comes to science, is people not being scientifically literate enough to understand that sometimes things change, and that is our best understanding at the time, and that may well end up changing in the future, but that doesn't mean the scientific method itself is flawed.
Exactly. So I'm not going to claim that the scientific method is perfect. I wish it would be faster, but there's a reason why it's so slow,
Mm-hmm.
in that the current method that we have will always catch bad science.
If done correctly, I assume.
If done correctly. It might take a while, but it always will catch that bad science, whether it's climate stuff, whether it's bad dinosaur stuff done by bad dinosaur paleontologists, whether it's, you know, weird genetics stuff going on over in like the biology side of things. It will always catch them and disprove them. And funnily enough, as much as I sort of don't like how big of egos people have sometimes in science, that is kind of an asset as well. Because when that one jerk publishes something massive that they may not have the data to support, a bunch of other people are like, I want to be the guy to prove that wrong. Just shut that guy down. I want to be that guy. So then they follow up on that and either prove him wrong or her, prove them wrong, or they say, maybe this person was onto something. And then they do more tests to figure out, was I onto something? They look at it at a different way. And that's how we get to some of these bigger conclusions, whether it's in paleontology, biology, you know, that's how like plate tectonics happened. You know, the concept that continents do move around on plates, that was complete nonsense up until like the 60s.
And it sounds like complete nonsense when you just like when you kind of think about it, like the land is moving around the Earth on like it sounds ridiculous until
Yeah.
until you have somebody explain it to you appropriately because of all of that good data. So, and I think that's kind of a good place for us to end off here, unless there's
Yeah.
anything else that you want to add on to what we've talked about.
No, this was all I could want out of this episode, talking about the scientific process, which is something that more people should know more about, especially these days with stuff like COVID. You know, science gets stuff wrong, and that's okay. You know, it's less okay because in this case, it likely resulted in the deaths of some extra people. But the bad science is always caught. Always.
The bad science is reason enough for good science.
Exactly. That's a really good way to put it.
And I think that's kind of a the place where we're going to leave off. And this has been, like you said, you got a lot out of this. I got quite a bit out of this, learning both about dinosaurs and then about the extinction themselves and the different eras, how we divide up different eras and periods of geologic history. This was been kind of fantastic. So thank you very much, Gavin. Everybody, keep an eye out next week for our Jurassic Park episode. And I think we can leave it there. Thank you very much, Gavin. I'll talk to you next week.
Of course, Mike. I'll see you then.
Wonderful. Take care, everybody.